This is the accelerating rate calorimeter that we use to characterize reactive chemicals. This technology was developed in the 1970s by Dow Chemical. They had a need to characterize reactive chemicals using small quantities in the laboratory prior to using very much larger quantities in an actual process. The big shell you see here on the outside is a containment vessel that's used to contain any possible explosions if you have a very exothermic and perhaps unexpected reaction inside the accelerating rate calorimeter. Inside the calorimeter is a very small vessel. You can see here on a close-up. The size of the vessel is about 10 cc's, 10 milliliters. There's also a thermocouple that attaches to the outside of the reaction vessel. These reaction vessels can be made out of a variety of materials, stainless steel, titanium, depending upon the temperature and pressure requirements that you need. The upper and lower parts here this is the upper heating element and this is the lower heating element, and both of these are controlled by a controller here on the very bottom of the base of the unit, and there's also an operator interface over here that's used for the operator to control the activity of the calorimeter. Now the idea here is very simple. What we do is we put the small chemical inside this reactor vessel, and then we heat it up over a period of time. It can be done in a variety of ways. One way is to heat it up at a constant temperature rate, let's say a couple degrees C per minute, and then we wait and look for any type of exothermic behavior. And once exothermic behavior is detected, then the calorimeter goes into adiabatic mode, trying to match externally the temperature inside this little vessel. From the information, we can get a lot of information that is used to characterize the reactivity of the chemical. We can first determine the reaction order. We can get the Arrhenius equation parameters, both the pre-exponential factor and the activation energy. We can also get the maximum temperature. We can also get the maximum pressure. We can also determine from the experiment the maximum temperature rate and the maximum pressure rates. This information is not a detailed kinetic analysis of what goes on, but it is enough for us to characterize the chemical so that we can use the chemical safely in the process. This information can also be used to size relief devices, to determine the area required for a relief device, and other types of designs that are needed to ensure the safety. Now typically also what we do is we heat the sample here at a temperature much higher than normal process conditions to ensure that there aren't any undiscovered or unknown exothermic reactions that occur, perhaps a decomposition or some sort of side reaction that perhaps could be even more hazardous than the reaction that produces the product that you're interested in. Large chemical companies such as Dow, BASF, and DuPont, they have requirements that all chemistry be evaluated in this fashion to ensure that they don't have any unexpected reactions. The technology is well developed. The analysis is very well understood. It's a very big part of a reactive chemistry program that is used by chemical companies to ensure that they understand the reactive hazards of all the chemicals that they are using in their chemical